So our next speaker is Eric de Kemp from the Geological Survey of Canada. And Eric is presenting to us Earth model construction in challenging geologic terrain, designing workflows and algorithms that make sense. Just a bit of background to Eric. Dr. Eric de Kemp is a 3D interpretation specialist with the GSC in Ottawa for the last 20 years. He was awarded his PhD in 2000 at the Université de Québec, Chicoutimi, and in 3D integration and visualization of structural field data, tools for regional subsurface mapping. Eric's research delves into 3D visualization and modelling of geologic structures, and his expertise in geological analysis is coupled with a strong background in the integration of geoscience using GIS and remote sensing technologies. His specialisation in pre-Cambrian field-based 3D studies combines stratigraphic, structural and geochronological analysis in complex regions of the Canadian Shield. He's currently a research adjunct at the University of Ottawa, and current research focuses on optimization of methods involving regional scale 3D geological interpretations and methods. Thank you, Eric.
Okay, thank you, Mark. Greetings, everybody, and thank you for staying on for the conference. We're ready for the final push here. Thank you to all the conference organizers as well. A lot of work goes into these things, as you know. And this special session as well for Mark, Lindsay, and Tim Chalk, who's not here. Thank you for getting all the papers together and all the editors that will eventually put things into the final compilation. And thanks, Glenn, for holding the fort here too. As Mark Jessel has done, I'd like to thank a whole pile of people that have been involved in the work that I've been doing over the last few years. Just a few of the names here in this contribution: Mark Jessel, Laurent Allier, Ernst Getzler, my colleague at the GSC, Mike Hillier, who does a lot of the computational modeling and the mathematical modeling, Mark Lindsay, and my colleague at the GSC, Boyan Broderick. So I imagine there's a fair number of people here that could call themselves 3D practitioners, but I think aside from being a specialist in 3D modeling, everybody is basically inherently doing 3D modeling, whether you're a geophysicist, a geologist, geochemist. We're trying to target things that are three-dimensional objects in space at various scales, whether it's at a mine scale or a large craton scale. We've learned quite a few things in the last decade since we've been together as a conference here about how to do 3D modeling. And I can say pretty much now that it's fairly normative doing 3D modeling, geological modeling at the scale of the mine site. Here we see an example of that, which is from a project that I've been involved in over the last few years. This is the giant Sullivan mine in Western Canada, in the Purcell Anticlinorium. This deposit here, we've pulled together thousands of drill holes, probably 30,000 holes to construct this model. And we have a workflow for doing this, which is pretty well under our belts right now. We know how to do that. But in the context of what we want to do exploration-wise, we want to move much further than just a single mine like this. That mine is this yellow dot, this yellow flake inside there, and it's sitting in what we call the LMC. This is a regional scale prospective horizon that we've also modeled, and this project's goal was to develop regional scale 70 kilometers by 100 kilometers by 20 kilometer model of that target horizon, which we have accomplished. And it was quite a challenge to do that. But what we have discovered in the process of doing that, which is the emphasis of my talk here, is to start to look at the heuristics of a workflow that will work best for doing that kind of thing. The other thing is, in going into this more regional scale, we're now entering into a much more challenging situation. We're now making 3D models in what I would call challenging terrain. And I'm going to talk a little bit about that in a few minutes. And the current workflow that we have for doing things at the mine scale, which I will call a linear workflow, needs to be looked at again and adjusted to perhaps what we will call a circular workflow. In going into these challenging areas, we're encountering geology that's complex. When we make our models, they need to be reflective of the geology that is sensible, that is reasonable. So we need tools to judge the reasonableness of our models. So I'm going to talk a little bit about what I'm calling a geological event manager as one of the components of checking that reasonableness. And I'm going to finish up with a little roadmap of where I think things are going in developing this workflow. So I want to define what we mean by challenging terrain. It's a very subjective definition. Every terrain, no matter if you're in a very simple Phanerozoic basin, can be challenging depending on the components that we're looking at, the kind of problems we want to deal with. Challenging terrain is really a function of the geology complexity and the data density that we have available to tackle that terrain. So here on your left is what I would call a complex geological situation at the outcrop scale. I think everybody can intuitively see that that is the case. However, to start to build models at regional scale, this is an example here from Becky Monsion's MSc thesis, which she's just completed, and congratulations again for your success in winning the R0 challenge with your group. This data was very difficult to integrate and level, and it's underlain by data that is very heterogeneously distributed. The red dots here give you an idea where the dense areas are and where there is lots of complementary data from different generations of folding, and it gives you an idea of confidence. But the models that are coming out of there, often we find that there's this relationship between the more simple parts of the model and where the data is dense. And generally, the more complex geology, as you see here in these Paleoproterozoic knap structures, are in areas where there is much less data. All right, so this is one of the key challenges for us to deal with in 3D modeling. Data is very precious. Wherever we have it, we need to use it to its maximum potential. The kind of problems we're dealing with will directly impact on what kind of workflow that we need in order to move forward. So data doesn't have to always be dense in the sense of a spatial sense. It can be very localized. However, it might be very dense in its content. So for example, here we can look at ice cores in Antarctica, and one single data point can have implications of how we interpret at a global scale. On the mine scale, we can have quite a bit of data, as we had in that Sullivan example, but it's very localized, and it's very difficult to extend spatially beyond the mine site, especially if the geology is very complex. So importantly in our workflow, we need a way of judging what is going to be geologically reasonable in our models. We need these first principles to be able to go back on, and one of the core things is if it is sensible in terms of all the relationships and the timings that are going on. And this happens all the way from the beginning of our modeling efforts, right from the time we're making physical models here to drawing cross-sections and conceptual diagrams, some conceptual diagrams that Sandy has shown. These things, we have to have methods for being able to take these concepts and the inherent relationships in them all the way into building the numerical model. This is especially true now because we're getting into very automated methods of building these geological models. It's very easy to put in data and push a button, as anybody that's built 3D models, and just, as you know, you can just make a surface or a collection of surfaces and bodies and come up with solutions. This example, I won't go into detail about it, you can read it in the paper, but here we have a collection of dips. The blue ones represent tops and reds bottoms, so they have polarity with them. And they're flipping back and forth at a high rate, but they're only representing a couple of horizons, three different stratigraphic horizons. And this is the control model. So you get a series of isoclinal folds that have been refolded in a coaxial sense. If we were to use our methods that we have in hand right now, this example from GoCAD SCUA, or we have an in-house tool which is called Surfy, or Leapfrog would have done the same. You get surfaces in here that actually are geologically impossible to get. They wind up contradicting the geological model, the geological history, because we don't have the ability to control that right now. So geological history and geological events are very important as we get into complex terrains. We have a series of events in every terrain that we're dealing with that needs to be managed and logged and taken into consideration during the modeling steps. This just example shows you that you can move from something that's encountered one tilting event here, and then even more deformation where you're overturning things and getting more and more complex as the deformation path increases to the point where we're getting this kind of complexity going on. So we need to take into consideration all of these things, because when we get into the interpretation stage, it has really profound effects on the end result. Just a quick example too there, showing you this deformation stages that need to be taken into consideration from the Cordillera. All right, so we need to support the full geological history. Those examples are stratigraphic examples of deformed horizons. Same story when it comes to intrusive, complex terrains. We need to be able to take into account the full deformation history and intrusive history that causes very strange topological relationships in the geometric model. All right. So complex geology, basically, to summarize that, is when we have multiple geologic events and they all conspire to make things complex, not simple. There are terrains that have protracted histories involving metamorphic events, not just burial history, not just the last few phases of deformation that need to be taken into consideration, and extensive tectonic influences. So we need to sum up all of these relative temporal geological relationships to unravel this event history. So in the end, whether we're talking about a map or a 3D model, we have to understand that they are simply spatial extensions of a lot of these relationships. And we can break down these relationships into binary relationships. So we need tools, algorithms, workflows that can be able to do that. Our data is sparse. We need to start having tools to define what we mean by sparseness and perhaps even quantify what we mean by sparseness. All of this sparse data situation in challenging terrains means that our models will be unconstrained. We need to be able to produce models that can use the sparse data directly in an automatic way, and we'll be able to make many different models. And because of that, we need to be able to have tools that will map and model the uncertainty associated with all those different suites of models that come from sparse data and complex terrain. All right, so in the end, sparse data is not going to be able to be very accurate in producing all the features that you think are in a given terrain. And there's always this rule of the Nyquist frequency that you cannot, create something that you're not sampling in a high enough density. But if you know enough knowledge about what the features are, you might be able to mimic them with different approaches. One of the approaches I've been using lately, the details are too much to mention here, but I've been working with what are called spatial agents. These are tools that are used in genomics and other domains for modeling things that are sparse and where we do actually have a lot of knowledge about the process involved in them. And I'm just showing a few pictures here of some of these agents that they can be used to model fold structures in a regional sense when we know a few dip informations, a bit of dip information for fabric trajectory analysis, and they can also be used for making surfaces, graphical surfaces dynamically in a model space. So we need to start getting used to looking at modeling in what I call an Earth model space. We can see it simply in terms of a knowledge axis here, where we know very little about our terrain on one side, and a higher side we know a lot, and in the data axis, where data is sparse or dense on the other axis. We may be in an extreme situation where we have absolutely no spatial data in an area, but we, perhaps through proxy or some other mapping in an adjacent area, we know quite a bit about the geologic history, and we can perhaps use some tools to create forward models. But that would plot right on this far axis. One example would be to use a program like Naughty, or to take some of our conceptual models and plot them there. Then we have maps, would plot more on this axis where we actually have data, but we use our own implicit knowledge in our head to map things, and I've done that with the example I showed earlier. But then we have automated modeling tools which use a little bit more data, but less of the knowledge, so they plot on this axis in here. We also do inversions, which are very data-driven, and they're further along this axis in here, and they can slide back and forth depending on how much constraints are put in there. And then if we look at this third axis here, we can look at the dimensionality of our models to describe them, 1D, 2D, 3D, and so on, and with properties embedded in them. And then we start to have what we often call common earth models or interpretive constrained models, as I like to call them. But the goal is, within this model space, to move further and further up this axis here and have things that are better constrained with data, but also with knowledge. This is a summary of the more linear workflow that we're familiar with at the local scale, at the mine scale. I won't go through all the details. You can read that in the paper. But essentially, what we have is a flow going from left to right, where we're dealing with 2D data for the most part, or 1D down drill holes, and we input that into some kind of GIS environment, and we move into a 3D modeling environment and go through a process of reclassification, interpolation, and eventually visualization and rendering. And also, there'll be some QA, QC, of course, on both sides. But that's essentially what is happening right now. It's a one model process. The 3D linear workflow, it's important that we have a way of standardizing and having a way to get a whole group of people to have a common practice. It can be repeated, and you can often get similar results. And you develop a community of practice. A team of people at a mine will know how to do these kind of things and can pass it on to new people that enter into the company. The problem is that when we add value to these models, it's very difficult to reverse the process and still keep that value. This is a big downfall of it. But in fact, the workflow that we really need, especially to go regional and complex terrain, is a circular process. We need a circular workflow. This example here, which Becky worked on after she's gone through a lot of pain trying to build her models, she discovered that it's actually not just a linear process, perhaps for a few features, but as you add more complex features, that workflow needs to become circular. So in that kind of approach, the emphasis on increasing the overall knowledge of the system. It's iterative, there's no start, there's no end, it's evergreen, and we create model suites, not just one-offs. And also in that context, uncertainty can be modeled and hopefully reduced. And there's always value that's being gained to the whole process. So in looking at a workflow that's sensible, it might be worth going back in time and looking about what makes a good geology map. We all know it is generally a good map. It sort of hits us intuitively. You get familiar geological forms and patterns that you're used to seeing in the field. They're often aesthetically pleasing. They have nice colors and contrasts on the paper, mean contrasts in process often. But importantly, they have geological meaning. And that's because there's embedded geological knowledge in a map, as a stratigraphic column, for example. So there's a consistent geological topology, and that means that the geological relationships are actually the most important thing that is being represented in a map. So we try to encapsulate this in what we call the geological event manager, which tries to keep these relationships intact. This is a quick summary of what we're trying to embed in them. And just, generally we try to see the map as an extended set of binary relationships, and that the event history is going to be consistent at all scales, whether we're at the mine scale or a regional scale, and that the things that you see in the map or in the model don't contradict basically physical processes, geological processes as we know them. So hopefully down the road we can have complex geological environments like this one here in this metamorphic terrain, and we'll be able to start to move into encoding these relationships in a much more exact manner. We have tools to do this from mathematics. For example, we have what are called Eigen Hoffer relationships that are used for mapping binary paired relationships. My colleague Ernst Getzler and I wrote this short paper at the IAMG conference just to show what are the minimal relationships topologically from the Eigen Hoffer perspective that are required. But also we have to go beyond that into what are the exact geological binary relationships in terms of sedimentary structural relationships, plutonic relationships. Right, this quick example here, we're seeing a relationship on a mega crenulation fold near a fault zone. So there we would have two events, an S1 event from a previous fabric being folded here in this crenulation. And that can be encapsulated in what we call a relation. And this relation can be used then in a modeling package to do a whole pile of different things. There's a body of work that's already been undertaken from the work of Carrie Burns, and now in work by people in Perth at CET. The thesis of Sam Thiel moved this along even further. And I won't go into all the details, but it's very exciting now to be able to see that we can start to encode fundamental geological overprinting relationships for a host of geological process into some kind of computer system. Also, we have another group working at Monash in Melbourne with Laurent Ellier's group. We have a number of theses and postdocs that have been done there to try to tackle some more complex geological overprinting relations from structural geology, like folding. All right, so just a quick snapshot here of an example of where we've encoded some of this more complex geology. And we have a number of matrices here that, show numbers of simple stratigraphic relations all the way from here, all the way down to complex intrusions and foldings and offsets that would be encapsulated in matrix form here. So this is where we have to go if we're going to be handling more complex terrain and building more automated models. We need to be able to quantify them, we need to be able to compare them. We have to have some way of indicating the complexity of our models and the quality of our models between different terrains and within a given area. So just to hammer home the point here you have a set of map relationships very early on in the game, very simple to understand. All right, and then we can encode them in terms of events and relationships. As we go along in the geologic process, we get more and more of these, but we retain all the relations that have occurred previously. So that in the end, we will be able to extract these and use whatever algorithms are appropriate for each stage of these events. All right, so you might get something like this, where you'd have a map, which to me is the same as a model. Whether this is a 3D or 2D map or a 3D model should make no difference. We should be able to reconstruct this map based on all the binary relationships and the constrained observations that we have there. So in summary, this is just a quick sketch diagram of what could be this kind of workflow. The workflow is centralized by this more circular process. It's driven by a data store that would include not just spatial data, but also event features and observations of those relations in the field where we do have them, driving everything. So we'd be going around this wheel where we're going through input to visualization to modeling, reconciliation of data, validation, uncertainty modeling, and model updating constantly in this circle, but that we would have an event manager controlling and making sure that geological reasonableness is being maintained through these event organizings. And then this would be more of a visualization, almost a secondary engine to what's going on here. And we would see no difference between 2D maps, representation, geological cross-sections, representations, and the 3D representation. And there wouldn't just be one-offs of these, there'd be suites of these coming out. All right, so it's iterative, many ways, many models would be the workflow. So the 3D workflow of the future, circular workflow, works in challenging terrains with sparse data. We would be able to do uncertainty modeling. We had a whole uncertainty workshop last Saturday focused on that. I would combine all the results of doing inversions or joint inversions. There'd be a way of assessing geological reasonableness, which tracks the geo-event history. It would be a simulation process environment for making models and maps. And in the long-term future, this is a long-term goal, there would be process-coupled modeling activities that would not make models that were contradictory to physical laws of nature, and various implicit codes and more codes that we can't even predict what they'll be right now. Importantly, as all the work that I've been involved with the last few years, it has to go ahead in a collaborative practice way, that where we can document what are the best practices to go forward. Thank you.
Oh, excellent talk. Thank you, Eric. And before we all disappear off to afternoon tea and the closing poster session, any questions for Eric?
I have not. That's where we need to go. I think we need more expertise to help out in that area. There's a whole body of expertise there, I'm sure, that needs to be brought into the table, for sure. Thank you. Yeah. Okay. Great. Well, we need to talk after, I think. Okay, great.
Yeah, just a follow-up to that, Eric. The circular nature of modelling, as you described, and iterative processes that you go through. I guess it'd be essential that what's been done to the data is recorded.
Yeah, exactly.
In what cycle and what's happened and where it's gone.
Yeah.
Do you see our current technologies able to do that?
I think they could do that. I just think in practice we don't. I imagine the pieces are in place to make that happen.
Okay.
It takes a lot more diligence, and especially if you're in the private sector world of consulting and the clock is ticking, you tend not to do that unless the infrastructure is in place.
Yeah.
But I think in the next round we're going to have to focus on how we get that practice going.
An automated record of
who's doing this interpretation, timestamp it. Every transaction that goes on in the bank, you better believe they know who did it, right? and how it was done when it was done. So that kind of tracking, I think, is available. You just have to get used to using it.
Yeah, sure. Any other questions before we close the session? No, I can't see any hands. Oh, well, look, I would like everyone to join me in thanking today's speakers, or this afternoon's speakers. I'd like to thank my co-chair, Glenn, for stepping in for Tim Chalk as well, and for everyone to coming to this session and taking part. Thank you very much, and hope you enjoy the rest of what's left of the conference.